Hi, in this video, we want to take a look at difference equations, specifically for the purpose of using difference equations to better understand time series. So our true goal is to understand time series better, and we're going to do that by using difference equations. Well, difference equations, in general, we're taking sequences and we're doing subtraction, and we've got coefficients, and what we're going to do is we're going to take the sequence, and which is deterministic. There's nothing random, nothing statistical, no probability aspect. That's deterministic. It's straight math. And we're going to understand these better. That way, when we get the time series, which we model with a sequence plus a random term, we'll have a better understanding of what's going on. So in a lot of ways, what we're doing is we're looking at effectively time series without the random components. All right, so what we're going to do, we're going to go ahead and run through time series analysis and its applications. This is the textbook. Here are the names of the authors. Here's our GitHub page. And the textbook can be downloaded for free through UCF's library, for free for any students. All right, so what we're going to do, let's jump straight into an example. Let's say that I have a sequence where the nth observation is equal to a constant, a coefficient, times the previous observation, and that constant's not equal to 0. Well, if we sit down and we work on this, we're going to see that this is very geometric. If I go through, and all right, here's u sub 1, it's just alpha times the first observation. U sub 2 is alpha times the previous, which is alpha squared times u sub 0, our baseline. U sub 3 is alpha cubed times the baseline value. And so very quickly, I see a pattern that u sub n is equal to alpha to the n times that baseline value. Okay. Well, now what I want to do, I want to invoke the backshift operator notation. That way I have more algebraic tools to analyze what's going on. So let's go ahead and do this. So I'm going to take this equation. Now you'll notice that here in this setup, I've got everything on the left-hand side. I have 0 to the right. When I'm working on it down here, I've got the nth term on the left, I've isolated, and everything else is on the right. So we're going to be doing this back and forth to whatever presentation is easiest in the moment. All right, so if I take this original equation and I apply the backshift operator notation, I notice that it's no backshift, that's b exponent 0. So remember that b is not a variable, this is actually a function on a time series going backwards in time. That's why we call it backshift operator. And then here I have alpha times backshift one time. All right, that's our operator notation for the same one. So now what we want to do is I want to take what I have for my equation and I want to get the associated polynomial. All right, well, here it's going to be the constant of 1 minus alpha times z. Okay, and so this is alpha times z. That parentheses is not the best place, but it's okay. And so we can see the root of our associated polynomial is 1 over alpha, very naturally. Okay, and alpha is equal to our root inverse. Okay, so now let's say I knew the initial value was c, some given constant. Now, for this particular problem, it's not a very big deal. It's not very interesting. I'm trying to baby step into harder problems. So let's say I know that u sub 0 is equal to c. The very first baseline value is equal to z. That's our initial condition. Then I know, and let's say I know the root of my polynomial, then u sub n is equal to our root inverse to the power of n times that initial condition. All right, so if I know the root of my associated polynomial and I know the initial condition, I know the entire sequence. I know all infinitely many listed out values. Okay, well now let's consider the autocorrelation of such a model, or of an AR1. All right, so if I take an AR1 model here, x sub n is similar to what we've looked at So x sub n is equal to a constant times the previous value plus some random term. Okay, so this is a little bit different than what we had a moment ago because I've got the random term on here. But wait. I look here. If I was to sit down and compute the autocorrelation like we did in a previous video, if I sit down and crunch it out, I see that I've got rho of h minus phi times rho of h minus 1 equals to 0. So in fact, even though I'm working in time series, here's an example of exactly this difference equation we were talking about a moment ago. All right. Now, next thing we can look at are degree 2 difference equations. All right, so we did degree 1. Let's kick it up a notch. That's always what we do in math. Once we figure something out, we make it harder. All right, so let's do a degree 2 difference equation. I'm going to say u sub n minus a constant times the previous observation minus a constant times 2 observations back. And I'm going to say that the coefficient for 2 shifts back is not equal to 0. And we're going to say that this equation holds for all numbers n equals 2, 3, 4, and so on. Okay, well, when I've got this, I want to figure out how to figure out the equation for this. So this one's a little bit more complicated. I've got more things happening. All right, so the author of the textbook gives an explanation. I like a different presentation. So the textbook goes a little bit different than I do on this one. Here, what I'm going to do is I'm going to use generating functions from combinatorics. And what I'm going to do is I'm going to convert this to an equation on series, on power series. And then I'm going to use the properties of power series to figure out exactly what are the terms in my sequence u sub n. All right, so when I do this to get my sequence, first thing I'm going to do, I'm going to multiply everything by x to the power of n. So let's say I have this equation. What I'm going to do, I'm going to multiply everything to the power by z to the power of n. Multiply everything by z to the power of n. And notice that n is matching the subscript here, the largest subscript I have in my equation. So now, after I do that, you notice that this subscript does not match that superscript. This subscript does not match this superscript. All right, so what I want to do on this next step, I want to get all of my n's to match up when I'm looking at added. So here, n and n, that's good, that's good. All right, we like that. I'm going to take one of these, and I'm just going to factor it out. When I factor out one of the z's, I notice I'm going to have n minus 1 as an exponent. I've got n minus 1 as a subscript, and here is that z that was there a moment ago. Over here, I need to get rid of 2 z's. Oops. I have too many z's, so I'm going to factor that out. And now my subscript matches my superscript. All right, I'm liking this. Now, here's what I'm going to do. Now I'm going to invoke infinite summation. All right, so this equation holds for any n 2 or larger. All right, now I'm going to do the summation for n goes from 2 to infinity. Now I'm invoking actual series. So when I do that, we see that I have a series, I have a series, I have a series. Now these are very similar. The difference is on the n minus 1, the n minus 2, and the n. Okay. Now, what I'm going to do here is I realize if I look at this summation, the subscript actually goes from 1 to infinity. It starts at n equals 2. Well, if I plug in 2, I notice that I get a 1 in the subscript and the superscript. All right, well, if I get a 1 in the subscript and the superscript, I'm just going to go ahead and change this up so that it starts at 1 and goes from 1 to infinity. So what do? I add inside the summation. Everywhere I see an n, I replace it with n plus 1. All right, so I've added inside that summation. What I'm going to do, I need to subtract on the indices on the outside of the summation. So here, I'm going to subtract a 1, subtract by 1. I'm going to subtract by 1. Now, infinity minus 1 is still infinity. It doesn't, but if I have a finite number of terms, I subtracted 1, I would change the value in that up top. Now here, I look at this, I notice that, well, n starts at 2. So in fact, this summation starts at index 0. All right, so what I'm going to do on the inside, I'm going to replace n with n plus 2. I'm adding 2 on the inside. I need to subtract 2 on the outside. So this 2, I'm going to subtract 2, and that becomes 0. And then I'm going to subtract 2, and infinity minus 2 is still infinity. All right, so now things are looking just a little bit cleaner. Here's what I'm going to do. I notice that I've got summation almost 100%, close, not quite, very close. I've got the summation, n goes from 0 to infinity, u sub n, z to the power n. So I have a series, an infinite series. All right, so what I'm going to do, I'm going to say, you know what? I'm going to let u equal whatever this is. Now, when we talk about this u, I have to restrict z to be on the interval of convergence. The interval of convergence, we're going to figure out later down the road. Our interval of convergence will be the smallest interval such that all my math works out correctly. Okay, now as long as that interval has positive length or positive diameter, because we're dealing with complex, positive diameter, then everything is good. All of this works out. I just have to have any interval diameter, any interval radius greater than 0. All right, so now when I do that, I notice that this part is u minus the first 2 terms. This is u minus the first, and this is u itself. So what I'm going to do, I'm going to rewrite these equations so that I notice that this part is u without the constant, without the linear term. This is u without the constant. And this is just straight u. Okay, so now what I'm going to do, I've just got a regular old, really middle school algebra problem once I get to this step. For this moment, for the moment, I have just a regular old college algebra problem. I'm going to combine like terms. All right. So I'm going to combine like terms. So I need to distribute my coefficients and deal with the parentheses, combine like terms. And you'll notice that I get a polynomial on z times u. And then I get another polynomial using initial conditions on z also. So now I'm going to rewrite this so that I get u by itself. Okay. So now, if I can figure out what is the series on the right, what's the power series or Taylor series, how it doesn't really matter. If I can find the series on the right, then I know that that's equal to u. Okay, so if I can find the series, then I can use that to figure out all my sequences. So what my goal now is to figure out what is the series on the right-hand side. All right, so we got 2 possibilities. You see the associated polynomial in the denominator. Either this will have 2 distinct roots, or it will be square and it'll have 1 root. We're going to do partial fraction decomposition from pre-calculus, and then we do partial fraction decomposition, and we're going to work out, and that's going to give us what we really want. Now, something that we're going to do whenever I do a calculus maneuver that results in a unknown constant times a constant, I'm going to absorb that into an unknown constant just to keep the notation cleaner for us as we work through. All right, so what I'm going to do, I'm going to say that my associated polynomial is equal to, so when we have 2 distinct roots, is equal to this factored version. You'll notice that if I say z1, z2 are the roots of my associated polynomial, then since this is a 1, then it has to look like this when I do my my work out the factorization. Okay, that's the only way it can work out. Okay, so now I know from partial fraction decomposition that this will have to be equal to something that looks like this. Now, we don't need to know what C1, C2 are at this moment. We're going to figure that out when we figure out the initial conditions. I'm going to get the structure of the model, then I find out what the actual C's are. Well, if I go through and I recognize very quickly that this is in fact geometric, this corresponds to the geometric series. So then boom, I just work through that calculus, boom, boom, boom. And you see that I can very easily work this, get down to here. All right, so when I see that I have geometric series, both of them, so I just convert it to geometric. Boom, I've got it. Boom, I've got it. Now, this is with regard to convergence on that interval. So I see that z has to be strictly less than 1 over both of the roots in magnitude for the geometric series to converge. Okay, so now I've got the series written this way. Now, when I look at this, I know that this term has to equal this term plus that term after being multiplied by the constants. So if I was to work this out, I know that the coefficients of each power of z have to equal each other on the left-hand side and the right-hand side. That's the big trick here, that all of the z to the, of the z's to the power of 5 have to equal each other on the left and the right. So if I have z to the power of 5, I know that the ones on the left has to equal the ones on the right. And so that means that for any given n, this is going to be my equation. So now I know the form of every single solution without having to crunch through it. This is awesome. So this is a great trick to work out details. Now, to figure out C1 and C2, what I have to do is I have to take the initial values and I just do some solutions. For the roots, remember, I have to figure out that associated polynomial, which is pretty easy. And then find the associated polynomial, find its roots. Now, if it's square, things get a little bit trickier. We go through the same process that I have u is equal to a partial fraction decomposition, but what's going to end up happening is that you can see that we have a degree 1 on the factor, and we have a degree 2 on the factor in my partial fraction decomposition when it's square. And you'll notice that we only have one root. I put z sub 0 for this. All right, so the trick here for generating functions is to recognize that this is in fact proportional to the derivative of this. If I take the derivative of this fraction, it's nearly the same as that fraction there. Okay, so there's a constant issue. Now this is where I'm going to have constants merging because I don't know what that constant is. When I take an antiderivative, then I'm going to have another constant pop out, but I don't know what this one is. So I'm just going to say, you know what, C2 is, the old C2 times the new popped out constant from the antiderivative. I just don't want to mess with it. It'll keep things cleaner if I just leave it alone. All right, so I recognize that this is the derivative of that. And so what I'm going to do, this is geometric series right here. So I write this as a geometric series. I write this as a derivative. Boom, I do that here. And I realize that this part is itself geometric series. So I replace what's inside the derivative with a geometric series right there. Now, I'm going to take a derivative. Now, it is critical that we are on the interval of convergence for this calculus to work out. If we're not on the interval of convergence, this doesn't work out. So I must absolutely make sure that the interval of convergence has positive diameter for this to work out. Otherwise, this is garbage in, garbage out. So you'll notice that on the interval of convergence, I can switch the order of limits, and it's okay. So I go ahead and do that. So the derivative is a limit. I have an infinite sum, which itself is a limit also. Switching the order of limits is not a trivial task. You can get complete gobbledygook in your mathematics if you do it at the wrong time. So I take the derivative here, and boom, I've got this. So now I just go through, I just start cleaning stuff up, make it nicer, make it easier. I now realize that that constant, the n equals 0 term, disappeared when I did the derivative. So we need to just do a little bit of modifications. And you'll notice that I get pretty much the same game plan, that once I get z going, or once I get down to here, z to the n, what I need to do, I need to match the coefficients of z to the n, left-hand side, right-hand side of the equation, and I get my solution. And it's similar but different because I have only one root to work with. Now, to double check that in fact this works, all right, so first what I'm going to do, I'm going to check if you go through and just work through this math. This is me plugging in the two root solution in to the original equation. So here's my proposed solution. I believe that this is the correct solution, and I want to plug it into here and solve it. Okay, so I just go through, I plug it. There's a little bit of tough sledding. It's ugly. I had to do this on pencil and paper. I couldn't do this in LaTeX while I was typing it up, but ultimately I see I got the right solution. Now let's do it the other way. So here is my solution when we have a square associated polynomial. I'm going through the same trick. I put things in. So now on this one, this is much easier if I use a factored form, if I use a square presentation of our associated polynomial. And you'll notice that when I match these up, negative a sub 1 is equal to negative 2 of the reciprocal of our root. Negative a2 is equal to the reciprocal of our root squared. And so then what I'm going to do, I rewrite the equation, our original equation, using the corresponding root representation of the coefficients. And I just crunch this out, and it works out exactly the way I want. There's a lot of terms, but the punchline is slap it in, rearrange the terms, boom, we see that 0 equals 0. So we believe that we are right, or we're very good at being wrong, one of the two, but I'm pretty sure I'm right. All right, so here's an example of an AR2 process autocorrelation function. So let's say that I have this equation. This is a degree 2 autoregressive process. Now I'm interested in the autocorrelation function, so I'm going to go through, I'm going to multiply everything by x sub t minus h. Okay. Now, what am I going to do? Well, I'm going to take the expected value because that'll give me the autocovariance. And so now I've got an equation for the autocovariance. I'm not quite done yet. Now, what we're going to do is I'm going to invoke a causal autoregressive process. If it's causal, then I can represent my x's in terms of the white noise. So remember, when we have a causal process, I can take the autoregressive portion and represent it using a series on the white noise. And so I'm going to invoke that here. So I replace this x with this infinite sum on white noise. Now, why did I do that? Well, you'll notice that I've got white noise times white noise. When I do this, when I distribute that, this w sub t, when I distribute that, I'm going to see that I have white noise times white noise. That means the autocovariance is equal to 0, means the autocorrelation is equal to 0. And so, boom, everything works out. Now, I'm going to divide by the auto covariance at 0 to give me the autocorrelation. And so then, boom, now I have a difference equation for the autocorrelation function. And so correspondingly, we get a difference equation. and we know initial conditions from things we've worked out, pencil and paper in previous videos. So then, boom, I know how to work out the details of the autocorrelation just from the associated polynomial and the initial conditions. Now, if we have complex roots, things get a little bit more interesting. Now, when we get a complex root, it's going to work out that the two roots are going to be conjugates of each other. That in that conjugate aspect, remember, if I have a real number equal to a complex equation on the right, I know that the imaginary part has to cancel out. Because of that, I know that the constants also have to be conjugates of each other. Now, if they're both real, that's fine. That it's not going to be much to write home about. And what we're going to do, we're going to invoke polar coordinates to make things easier. So I'm going to say that my roots are equal to the magnitude times e of theta times I. And the conjugate, I'm just going to change the argument. I'm going to change the angle in polar coordinates to the negative. And if I do that, I can get a quick and easy equation to work out if I just remember what's going on. Now, when I do this, A and B are going to be new constants to work with to solve using initial conditions. But here is that punchline so beautifully. All right, so let's go ahead and take a look at an example. Let's say I've got this autoregressive 2 process. We got variance of 1. If I look at the associated polynomial, I see that my roots are 1 plus or minus I over square root 3. Now I'm leaving it in the bad notation in college algebra just to make it a little bit easier, makes the arctangent a little bit easier to compute, in my opinion. So when I take the inverse of 1 over square root of 3, the ratio of the real and imaginary parts, I see I get pi over 6. Well, pi over 6 is the same as 2 pi over 12. Remember, 2 pi is the period of sine and cosine. So I'm going to go with 2 pi over 12 instead of pi over 6, because this gives me that I see 1 over 12 cycles per unit time. Now, R will very nicely work out a lot of details for us if I just give us the coefficients of the associated polynomial, get the polynomial root. And so here is the first root. And so here it is, 1 over square root of 3 times I is the imaginary part. And so we can grab the argument, and 1 over the argument gives us the period, which is what we just worked out a moment ago. But here we can see we can do the same thing. Instead of pencil and paper, R will compute it for us. And so now let's go ahead and simulate a time series with these features. Here is my autoregressive coefficients. Notice that I dropped the 1 in here. That's important. I'm going to say I want 144 of them, and with a period of 12. And we're using TSA's ARIMA simulation function. And so here is a simulation of the autoregressive process that we created. And so now let's go ahead and compute just off the coefficient. So I don't need to know the actual time series. I don't need the data. I can go and I can actually use the theory we just worked out to figure out the autocorrelation function. So let's go ahead and do that. So here I'm going to use the ARIMA autocorrelation function and this is base R. I drop in the coefficients. Notice that 1 is missing from there. I don't have a moving average portion. And I'm saying go out to a maximum of 50. And then we just go through and plot. And so here we can see the pattern of our autocorrelation. Now, something that we can do is that we can convert our autoregressive model to a moving average model, as long as it's causal. And I'm doing the same thing. And then I'm going to go through and I'm going to do my time series plot. And so here we can see the weights that are coming out from this. All right, so now let's go ahead and think about how would we compute those weights for an ARMA model? So I want to be able to take the autoregressive portion of an ARMA model, and I want, because it's causal, I want to compute the time series on the white noise forming. Well, if I sit down and work it out, I can see if I have this equation here, so autoregressive moving average model, moving average is on the right. What I'm going to do, I'm going to set psi sub 0 equal to 1 because both sides will have a 1 in their associated polynomials. And then I'm going to start, whenever appropriate, whenever it makes sense, I'm going to set psi equal to the coefficient on the right-hand side. And then psi will be equal to 0 everywhere else. And then I'm going to work out the details going forward. Now, for large enough of values, large enough of subscripts, psi will be equal to 0. And we can work this out by hand, and we can also work this out using the ARMA to moving average function in base R. So here's an example using 0.9 and 0.5. This is one that I worked out the details by hand in a previous video. And here we can see the weights decreasing because of that geometric aspect. Well, that's all I've got for you. Math is short. Life is short, do math.